All right, friends, let's look at some examples in determining continuity. So in this case, we're just going to test for it. We're not going to label what kinds of discontinuities. We'll do that in a minute. Right now, we're just going to talk about checking our three tests. So here's our first example. So I have f of x equals x squared minus 4 over x minus 2. And the question is it continuous at x equals 2? Yes or no? So remember, our very first test is, does f at a exist? So in this case, we're going to say f at 2. And we just plug 2 in, and I get 0 over 0, which is, and does not exist. So we don't need to go on any further. It's not continuous because it fails that first value there. Next, here's a piecewise function. These are tricky. So let's see what we got here. So we're going to do our test here. We've got at x equals 3, we're asking if it's continuous. So it sounds like we need to check what is f at 3. So if it's a piecewise function, I need to see where does the 3 go. Is it this top function or the second one, or there can be more, but which one does it go in? Here's the equals 3 part. So then I can plug this in and I get negative 9 plus 4, which sounds like negative 5. So does it pass the first test? Yes, it exists. So the next thing we need to do is we need to check the limit as x approaches 3 of our function. So this means we're approaching from, we need to check our values. So in order to do this, we need to do our two one-sided limits. So let's look at, I put a plus there, oops. Let's look at our function as we're coming from the right side this way, meaning our x values are larger than 3, approaching 3. And it looks like we would still be in this function up here because this says, I'm sorry, I'm not looking. It's this function, x greater than 3. That's the one we're looking at. So as I get closer and closer to 3 on this function, it looks like I would have 4 times 3 is 12. 12 minus 8 is 4. So it looks like I'm getting closer and closer to 4 as I'm coming this way. And then we would check the limit as x approaches 3 from the left. And so then that is going to be the top one because this is less than 3. And so then this would be our negative 9 plus 4 would be negative 5. That's the limit. It also happens to be the value there, and that's what we computed earlier. Now look here. Do these values agree with each other? They don't. So this is, as we thought, a piecewise function. It's going to two separate places. So then this limit, the two-sided limit, does not exist, and so we fail. So this is not continuous at 3. Let's try another one. So this says, I didn't write the thing here. Is this continuous at 1? X equals 1. So then, it's, I said 1, 0. Sorry, friends. So at x equals 0, why is there vultures flying over me? Oh, I don't know. That doesn't bode well for our math lesson when the vultures are circling. At x equals 0, it's defined right there. So f at 0 is 1. So there we pass that. And then the second one is what is the limit as x approaches 0, the two-sided limit. And we've already, I'm putting a check here. I was a little premature there, but we've already evaluated this, my friends. You know what this is. We did the table with this. So this goes to 1. And if you can graph that, or you can, that's just, we've already done that work, so we know. So now look, is the function defined at 0? Yes. Does the function have a two-sided limit at 0? Yes. And then the last thing we check is, do those two, I'm not the vultures, it's the vultures. Those two things have to equal each other. And 1 equals 1, and so the answer is yes. So this function is continuous at 0. So that's kind of a one way of asking the questions, is just a yes or no. Is it there? Is it continuous at a point? Another way is to say, hey, can you tell me where this function is discontinuous? So in this case, they're just showing you a function. What x value has a discontinuity? And you would see, well, the numerator has no problems, but if I look at the denominator, so it looks like x equals 5 would make this discontinuous. So we would say at x equals 5, there is a discontinuity. Continuity. All right, friends, let's look at classifying some of these here. So we want to think about these examples. We already did them. So the question is, first of all, is there a discontinuity? And then you have to determine what kind of discontinuity. My advice is always to, you can figure out if there is one algebraically fairly simply. But then if you need to say what it is, you probably need to graph. It would be the simplest way to do this. In this case, this was our very first example we had before, and we see that this has it's only undefined at one place, which was x equals 2, right? So we would say that at x equals 2, there is a discontinuity, and what kind would it be? Well, this would be a removable discontinuity, because there's a hole there. And you can say removable whether there's the hole is just a hole and it's not defined anywhere else, or if it is defined somewhere else and there's that gap or hole still there, those can still be removable discontinuities. On this one we evaluated, and remember, if we looked at the two-side limit, they didn't match. So at x equals 3, this has a jump discontinuity. And if you'd graph that, you would see that. And here's a different one. This is one we haven't done here. So what kind of discontinuity happens here at x equals -1? And I think you see that we're going to have the denominator going to 0. And you guys already know algebraically that's going to result in an asymptote, a vertical asymptote. So we would call this at x equals -1, we would call this an infinite discontinuity, because it's going to have that vertical asymptote there. And let's see, what else do we have here? Oh, just a super simple IVT problem. We're going to do this later on when we're studying, but we're just kind of introducing it now. So here's a function, x minus cosine x. And over this closed interval, we want to say, is there a 0? Is there a 0 in between those values? So what we do is we test the ends, right? If you remember that. So we're going to test this end of this interval and that end, and that'll get us some y values. So in this case, we're asking if there's a 0. So I'm hoping that the one end will be a negative value, the other end will be positive, and then we can confirm that, yes, to go from negative to positive over a continuous interval, you have to cross 0, right? And we look at this, and is there any discontinuities here? No. X is defined every place. Cosine of x is defined every place. So there's no discontinuities here. So this is a continuous function. Check. Remember, we have to check those two things. Continuous, and this is a closed interval. I think you want to be very careful, because some certain person might put open brackets at some time and ask you to do some IVT work. And if that ever happens, you say, no, I can't do it because that's not a closed interval. So let's check. So let's check first at f at 0. Let's check this value first. So when I plug 0 in, I get 0 minus cosine of 0 is 1. So 0 minus 1 is -1. And then we're going to test the other end. We're going to get pi over 2. So if I plug pi over 2 in, I get pi over 2 minus cosine of pi over 2 is 0. So I'm going to get pi over 2 minus 0, which is pi over 2. And as we hoped, look, this is a negative value. That's a positive value. So because this thing is continuous, does there have to be a 0? And in this case, they didn't ask us to find it, or them, because remember, there could be more than one. So our answer is simply yes, per the IVT. That's our answer, because IVT says if this is continuous, if that's a closed interval, and you have a value in between these two, it exists. There's an x value that exists. There's an intercept that exists.